Okay, we'll be presenting a subject very near and dear to me, boron treatment. Ooh. Okay, so the gist is that it uses the hydroboration oxidation reaction. Now, what is that? It was discovered in 1900s by Professor Brown. He won the Nobel Prize subsequently. But the point is, if you have these molecules that use boron but are also organic in nature, so they're called organoboranes, right? They have boron, which is not found in nature, but they also look natural, right? You can do cool stuff to actual organic compounds. If you don't know, organic compound just refers to anything with carbon, hydrogen, oxygen. Those are pretty natural, pretty biological. So if you use organoboranes to manipulate organic compounds, you can do stuff like change carbon double bonds. Yeah, that's pretty much all I know. So he used it. I mean, he proved that it could be used to do like vitamin synthesis, which is like fairly useful. But who cares about being healthy, eating well? All we care about is speed cubes, better speed cubes. So the thing about plastic is that the plastic that's used in Rubik's cube is ABS plastic, and that stands for acrylonitrile butadiene strenine. Okay, so each of these, as you can see, are organic molecules. So if you use boron and then you break, oh, look at that thick triple bond, look at these thick double bonds. If you break these, then okay, if you call back to your bio, your membrane, your cell membrane, the less double bonds it has, the more unsaturated fat there is, the less double bonds means that it's more fluid and more liquidy. And the more saturated it is, the more like fatty. Okay. So like if you think of peanut butter, you have that oil on top. That's the unsaturated fat. That's the liquidy, flowy, good stuff. And like also olive oil, right? Olive oil is very liquidy. It's unsaturated fat. It's very good for you. But then you look at like solid fat and like bacon or steak, right? And that's very bad for you. And that's saturated fat. So if it's saturated, i.e. it has more carbon double bonds, then it's more solid and it's more resistant. So if you take a speed cube, you break down the plastic, break down the double bonds, then you'll get the good. You'll get the good. And so yeah, onto the actual science behind it. You use the okay. So you have some random organic molecule here, right? Carbon double bond. Who cares about carbon double bonds? We want to break it. So you use a boron reagent. This is borane. I think it's borane tetra hydro tetra some BS. I don't know how to name chemicals. Okay, but basically you have some boron reagent. You have tetrahydrofuran, which is a solvent, not actually relevant, just something that this can dissolve in. And then, okay, so it adds, and then whoa, look at that, the carbon double bond broke. Now you have a hydrogen attached to this, that's kind of superfluous, and you have a BH2 attached to this. Now, BH2, not organic, we want an actual organic thing. So then we add some hydrogen peroxide and some hydrogen ions. Wait, no, not hydrogen ions, hydroxide. This is basic, okay? Like you, who's watching this. Anyways, then you break. I mean, no, sorry. The carbon double bond's already broken. You just replace the BH2 with an OH. And the OH is if you remember from bio again, hydroxyl group, which means it's an alcohol, which means we can get wasted off it. Not actually. But this to this in our speed cube metaphor is just making it more safe so you don't have the boron. That's kind of sketchy. But that's the good, okay? We go from carbon double bond, no carbon double bond. That's some good. So Christian was the one who popularized this method. He used sodium borohydride as his boron reagent. It's this. Yeah, water ruins reactions, so don't have water. Anyways, that's not the point. He used aluminum chloride hexahydrate as a catalyst. Now the thing about this is that he claims, it's a Lewis. It's not a Lewis acid, at least according to Wikipedia. But it's also a neurotoxin, by the way. So yeah, don't fucking snort it. You want to okay. So you know how there's THF there, but THF is like similar to acetone. Okay, it dissolves plastic. So you want a ratio of methanol to THFs. Methanol is just wood alcohol. Again, you can get wasted off it. Don't actually get wasted off it. It will make you blind. But the ratio of methanol to THF is approximately 65 to 35. This is pretty arbitrary, and it just is so that like the reaction can happen, but the plastic won't dissolve. And okay, another thing he says, fake news. He's like, The stuff you buy at grocery stores, that's like 2% hydrogen peroxide. You need like 30% or higher. Higher if possible. But the thing about that is, if you read the literature, as I am an intellectual and I do, yeah, okay. If you read the literature, as I do, because I'm an intellectual, you'll find that if you change the concentration of hydrogen peroxide from 30% to 15% to 12%, as long as you have enough molarity, which, if you remember from your chemistry, means the number of molecules, stuff like that. It doesn't matter. But if you have enough molarity of hydrogen peroxide, that's the only thing that matters. Concentration, fake news. So if you can use like 12%, that's what I use. That's fine. Now this is aluminum chloride. It rearranges to this thing plus salt. Now you'll notice that if it rearranges, then it's not actually a catalyst, which is what Christian was saying, which I didn't write in the slide, but whatever. Okay. So if you remember from your bio or your chem, a catalyst is something that helps the reaction but is not consumed. But no, it's not really a catalyst if it is consumed. It just speeds up the reaction and is consumed. So you gotta re-add it every time. This reaction should be done at room temp. That's pretty good. And it should be air safe, which means there should be no oxygen, which ruins the reaction. But yeah, no, it's kind of hard to do at home, right? So this is my experimental setup. I know I'm a god. I whipped this up in like a minute. But you have a mason jar here. Now, why did I use a mason jar? Because I was thinking about it and I was like, oh, it's like fermentation, right? So you take a mason jar. You have this glass weight here. Okay. Let's go in order. You have the mason jar. You have this nipple-looking plastic lid thing. Now that's so that gases can come out, but oxygen can't come in. Because when you're doing a fermentation, you're essentially trying to make an anaerobic environment for bacteria to grow, but not for for bacteria to grow, but not for like bad bacteria to ruin your fermentation. So you have this nipple thing which allows gas to come out, like hydrogen. When fermentation happens, the bacteria is gonna do some, what's it called? Opposite of photosynthesis. Breaking down of glucose into respiration. Okay, yeah, the bacteria is gonna respirize. When that happens, it's gonna release carbon dioxide and oxygen. No, just carbon dioxide. It's gonna release carbon dioxide. So this nipple thing allows carbon dioxide to come out and oxygen not to get in. So this is good for me because my reaction should be done air safe, so there's no oxygen coming in. Shoot. Now you have this glass weight here to keep the cube underwater. This cube should be broken up. This is just me being lazy. So you have your solution here represented by the liquid. You have your solution. You have your glass weight. You have your cube underwater undergoing the reaction. So that prevents it from going. Yeah, it contains the reaction basically, and you have ice, water. You have a pan. You have a pot. You have water, you have ice, and then so that keeps it cool because it generates a lot of heat. It's very exothermic. The enthalpy for sodium hydroxide and water is pretty high, and the same for sodium borohydride and water. It's kind of shaft. I did experiment, as you can watch from my YouTube video. Kind of worked, kind of didn't. It's really sketchy. I thought I was gonna die. The smell of methanol or THF or whatever it is very strong. It definitely should be done in a lab. Don't do it at home. Don't do it in general. It's not good.